Hello friends, welcome back to my channel. Today I would like to talk about acid-base equilibria. These are some of the common acids: hydrochloric acid HCl, sulfuric acid H2SO4, nitric acid HNO3, ethanoic acid CH3COOH. And these are some of the common alkalis: sodium hydroxide NaOH, potassium hydroxide KOH, ammonia NH3. A base that is soluble in water is called an alkali. BRØNSTED-LOWRY theory of acids and bases. A BRØNSTED-LOWRY acid is a proton donor. A BRØNSTED-LOWRY base is a proton acceptor. So here comes an example. HCl plus H2O gives you H3O plus Cl minus. As you can see here, the proton H plus is donated by the hydrogen chloride and accepted by the water, forming the positive hydroxonium ion and leaving a negative chloride ion. An acid is a proton donor. Hydrogen chloride is the acid in this reaction. A base is a proton acceptor. Water is a base in this reaction. Remember that a proton is a hydrogen ion, H+. This is the second example. NH3 plus H2O gives you NH4 plus and OH minus. The proton H plus is donated by the water and accepted by the ammonia, forming the positive ammonium ion and the negative hydroxide ion. Water is the proton donor, it is the acid. Ammonia is the proton acceptor, it is the base. Substances like water, which can act as either acids or bases, are described as amphoteric. As you can see here in the first equation, water acts as a base, whereas in the second equation, water acts as an acid. BRØNSTED-LOWRY acids and bases do not have to involve aqueous solutions. For example, when chloric 7 acid HClO4 reacts with ethanoic acid CH3COOH in an inert solvent, the following equilibrium is set up. In this reaction, HClO4 is the acid because it is donating a proton to CH3COOH. CH3COOH is the base because it is a proton acceptor. Conjugate acid and conjugate base pairs. When ammonia gas dissolves in water, the reaction that occurs is reversible. Ammonia plus water gives ammonium ion and hydroxide ion. In the forward reaction, water is acting as an acid because it has donated a proton, and ammonia is acting as a base because it has accepted a proton. In the backward reaction, OH minus is acting as a base because it has accepted a proton, and ammonium ion is acting as an acid because it has donated a proton. Therefore, OH minus is the conjugate base of the acid water, while NH4 plus is the conjugate acid of the base NH3. In general, every acid has a conjugate base. This is the particle left when the acid has given away its proton. Every base has a conjugate acid. This is the particle left when the base has accepted a proton. In this equation, you can see acid plus base gives conjugate acid and conjugate base. One conjugate pair is HA and A minus, and the other conjugate pair H2O and H3O plus. Alternatively, the acid 1 base 2 terminology can also be used. HA is acid 1 and A minus is base 1. They are one conjugate pair. H2O is base 2 and H3O plus is acid 2. They are another conjugate pair. Strength of acids and bases. A strong acid is one which dissociates completely in a solution. HCl plus H2O gives H3O plus and Cl minus. This produces high concentration of hydroxonium ions. Therefore, the pH of the solution is very low, pH approximately equals 1. Examples of strong acids are HCl, H2SO4, and HNO3. A strong base is one which dissociates completely in a solution. NaOH plus aqueous gives NaOH aqueous. This produces high concentration of hydroxide ions. Therefore, the pH of the solution is very high, pH approximately equals 14. Examples are group 1 metal hydroxides. A weak acid is one which dissociates partially in a solution. CH3COOH plus H2O gives CH3COO minus and H3O plus, which is a reversible reaction. This produces very low concentration of hydroxonium ions. The position of equilibrium is far over the left. Therefore, the pH of the solution is higher, pH approximately equals 3. Examples are organic acids. A weak base is one which dissociates partially in a solution. NH3 aqueous plus H2O gives NH4 plus and OH minus. This produces very low concentration of hydroxide ions. The position of equilibrium is far over the left. Therefore, the pH of the solution is lower, pH approximately equals 12. Examples are ammonia, amines, and some hydroxides of transition metals. Strength of acids and bases is defined in terms of degree of dissociation, while concentration is defined as the number of moles per unit volume. Therefore, a weak acid in high concentration is still classified as a weak acid. Also, a strong acid in low concentration is still classified as a strong acid. Distinguishing a weak acid from a strong acid. Strong and weak acids can be distinguished from each other by their pH value using a pH meter or universal indicator, electrical conductivity, reactivity. When making these comparisons, we must use dilute solutions of strong and weak acids of the same concentration. pH values. An acid dissociates into hydrogen ions in solution according to Ha gives H plus and A minus. The stronger the acid, the greater the concentration of hydrogen ions, and therefore the lower the pH. We can determine pH by dipping a pH electrode into the solution of the acid. A pH meter connected to the pH electrode shows the pH value. Dipping a universal indicator paper into a solution of the acid and noting the color change. We then compare the color with that on a chart which shows the colors at different pH values. These are the pH values of some typical strong and weak acids and bases. Hydrochloric acid, ethanoic acid, sodium hydroxide, and ammonia. Electrical conductivity. Dilute solutions of strong acids have greater electrical conductivity than those of weak acids of the same concentration. This is because the concentration of hydrogen ions and other ions is greater in strong acids. We can determine electrical conductivity by dipping a conductivity electrode into the solution of the acid. A conductivity meter connected to the electrode shows the conductivity. Reaction with reactive metals. Dilute solutions of weak and strong acids of the same concentration have different reactivity with reactive metals such as magnesium. When a piece of magnesium ribbon is added to a strong acid, a steady stream of hydrogen bubbles is observed. Mg plus 2HCl gives MgCl2 and H2. When we add a piece of magnesium ribbon to a weak acid of same concentration, only a few bubbles are observed. This is because the concentration of hydrogen ions is greater in strong acids. Indicators and acid-base titrations. An acid-base indicator is a dye or mixture of dyes that changes color over a specific pH range. In simple terms, many indicators can be considered as weak acids in which the acid and its conjugate base have different colors. For example, HIN gives H plus and IN minus. Adding an acid to this indicator solution shifts the position of equilibrium to the left. There are now more molecules of color A. Adding an alkali shifts the position of equilibrium to the right. There are now more ions of color B. The color of the indicator depends on the relative concentrations of HIN and IN minus. The color of the indicator during a titration depends on the concentration of H plus ions present. Indicators usually change color over a pH range of between 1 and 2 pH units. In the middle of the range, there is a recognizable endpoint where the indicator has a color in between the two extremes of color. For example, bromothymol blue is yellow in acidic solution and blue in alkaline solution. The color change takes place between pH 6 and pH 7.6. The endpoint, which is a grayish-green color, occurs when the pH is 7. These are some of the chemical indicators used to monitor pH with their pH ranges of use and pH of endpoint: methyl violet, methyl yellow, methyl orange, bromophenol blue, bromocresol green, methyl red, bromothymol, phenolphthalein, alizarin yellow. A strong acid, strong base titration. Figure below shows how the pH changes when 0.1 mole per dm cube sodium hydroxide, which is a strong base, is titrated with 0.1 mole per dm cube hydrochloric acid, which is a strong acid, in the presence of bromothymol blue indicator. The results shows a sharp fall in the graph line between pH 10.5 and pH 3.5. In this region, tiny additions of H plus ions result in a rapid change in pH, a midpoint of the steep slope at pH 7. The midpoint of the sharp fall corresponds to the point at which the H plus ions in the acid have exactly reacted with the OH minus ions in the alkali. This is the end point of the titration. Bromothymol blue indicator changed from blue to yellow over the range 7.6 to 6, where the slope is steepest. Because there is a sharp change in pH over the region pH 3.5 to 10.5, we can use other indicators that change color within this region. For example, phenolphthalein changes color in the pH range 8.2 until 10. Because a sharp pH change occurs over such a wide pH range, there are many indicators that can be used to determine the endpoint of the reaction of a strong acid with a strong base. Figure below shows how the pH changes when 0.1 mole per dm cube aqueous ammonia is titrated with 0.1 mole per dm cube nitric acid, which is a strong acid. This is a titration between a strong acid and weak base. The result shows a sharp fall in the graph line between pH 7.5 and pH 3.5, that the midpoint of the steep slope is at about pH 5. Because there is a sharp change in pH over the region 3.5 to 7.5, we can use methyl red as an indicator for this titration. This is because methyl red changes color between pH 4.2 and pH 6.3. Values that correspond with the region of sharpest pH change. Phenolphthalein would not be a suitable indicator to use because it only changes color in alkaline regions, which is pH 8.2 until 10, that do not correspond to the sharp pH change. The phenolphthalein would change color only gradually As more and more acid is added, instead of changing suddenly on the addition of a single drop at the end point. Weak acids with strong base. Figure below shows a pH change when 0.1 mole per dm cube aqueous sodium hydroxide is titrated with 0.1 mole per dm cube benzoic acid, which is a weak acid. The results show a sharp fall in the graph line between pH 11 and pH 7.5, that the midpoint of the steep slope is at about pH 9. Because there is a sharp change in pH over the region pH 7.5 to 11, we can use phenolphthalein as an indicator for this titration. This is because phenolphthalein changes color between pH 8.2 and pH 10, values that correspond within the region of sharpest pH change. Methyl orange would not be a suitable indicator to use because it only changes color in acidic regions that do not correspond to the sharp pH change. The next one is weak acids and weak bases. Figure below shows how the pH changes when 0.1 mole per dm cube aqueous ammonia, a weak base, is titrated with 0.1 mole per dm cube aqueous benzoic acid, which is a weak acid. These results shows that there is no sharp fall in the graph line. No acid-base indicator is suitable to determine the endpoint of this reaction. In the example shown, bromothymol blue starts changing color when 19.50 cm cube of acid have been added, finishes changing color when 20.50 cm cube of acid have been added. Such a gradual color change on addition of acid is not good enough when you need to be able to read the endpoint to the nearest 0.05 cm cube. And that's all. Thank you so much for watching this video.